Have you ever looked at a really complex machine and just wondered, how do all those parts know what to do? How do they all move in perfect harmony? Well, it turns out there's a kind of hidden language, a grammar, that controls how everything moves from a simple bike to a massive factory engine. And today, we're going to learn how to speak it. Just look at this thing. This is a classic beam engine. You've got this giant wheels spinning over here, this huge beam rocking back and forth, a piston pumping up and down. It looks so incredibly complicated, right? But believe it or not, it's all built from just a few surprisingly simple rules. So how does it all work together so perfectly? And what if I told you that this incredible piece of history, this 200-year-old engine, actually follows the exact same fundamental principles as the engine in your car right now? There's a universal logic at play here, and we are going to decode. To understand the language of machines, we've got to start with the alphabet. These are the absolute most basic building blocks of all mechanical motion. So the very first letter in our new alphabet is the link. Now, a link is basically any part of a machine that moves. But, and this is the important part, it can't just be any old object. It has to be what's called a resistant body. That's just a fancy way of saying it has to be strong enough to push or pull without bending or breaking. A steel rod, that's a link. A rope, as long as it's pulled tight, yep, that's a link too. Even the hydraulic fluid in your car's brake line, that can act as a link. And here's what's so cool. On the left, you see how engineers draw these things? Just simple lines and circles? But on the right, you see the real deal, a heavy-duty piston and connecting rod from an actual engine. Engineers take these complex, real-world parts and boil them down to their simplest form to understand how they work. Okay, so if a link is a letter, a kinematic pair is what you get when you stick two letters together. It's really just two links touching each other. But here's the key. Their movement has to be controlled. It's constrained, so they can only move in a very specific, predictable way relative to one another. And this table really gets to a super important point. When you connect a bunch of links, are you building a machine or a structure? The difference is one simple thing: motion. In a machine, you want the parts to move. That's how they get work done. But in a structure like a bridge truss, movement is the enemy. Those parts are designed specifically not to move. Their only job is to carry a load. All right, so we've got our alphabet down, links and pairs. Now it's time to learn the grammar. Let's see how we can string these things together to create motion that actually does something useful. And this right here, this is the secret sauce of all machine design. It's not just about creating movement. The real genius is creating predictable movement. Uncontrolled motion is just chaos. It's useless, maybe even dangerous. The goal is to constrain every single part so it does exactly what you want it to, every single time. So check this out. This is a perfect example of what you don't want. You've got a round shaft in a round hole. What's it going to do? Well, yeah, it can slide back and forth, but it can also just spin around. Its motion is incompletely constrained. If you push on it, you don't really know what's going to happen. And that is not a good machine. Okay, but now look at this. A square bar in a square hole. Simple, right? But it changes everything. Now, no matter how you push on that bar, it can only do one thing: slide. That's it. It can't rotate. The geometry itself has completely constrained its motion to one predictable direction. This is the bedrock of countless machines. All right, now for a really clever engineering trick. What about this shaft in a simple bearing? Sure, it can spin, but what's stopping it from just popping right out of the hole? It seems unconstrained. But what if you add an external force, like the weight of a heavy wheel on top of it? All of a sudden, it's predictable. It can only spin. This is called successfully constrained motion, and it's a slick way to use forces, not just shapes, to control movement. So you might be thinking, how do engineers know if their combination of links will actually work and just be a floppy mess? Well, believe it or not, there's a simple formula for it. We're not going to get bogged down in the math, don't worry, but this table shows the gist of it. 3 links, like a triangle. The formula tells you it's locked solid. It's a structure. 5 links, it's an unconstrained wobbly mess. But 4 links, that's the magic number. It's a constrained mechanism, the basis for literally thousands of machines. Okay, we've got the alphabet, we've got the grammar. Now for the payoff. Let's start writing some full sentences and see how we can create real working machines from these parts. This is the last absolutely crucial piece of the puzzle. A loop of 4 links is a kinematic chain, but right now it's just kind of floating in space. To make it a useful mechanism, you have to fix one of those links to a frame. You have to nail it down, so to speak. That fixed link becomes the anchor, the reference point that all the other motion happens around. And this leads us to one of the most brilliant, kind of mind-bending ideas in all of mechanical engineering. It's called inversion. It means you can take the exact same set of links, but create completely different machines, just by changing which link you decide to fix to the frame. It's like mechanical alchemy. It's amazing. Let's use the most famous mechanism of all as our example, the single slider crank. This thing is everywhere. It has 4 links. You've got the frame or the engine block, that's link 1. The rotating crank is link 2, the connecting rod is link 3, and the sliding piston is link 4. This is the heart and soul of nearly every piston engine ever made. Now, in a normal engine, we fix link 1, the engine block. But what happens if we take the exact same parts and choose to fix a different link instead? Watch what happens. For our first inversion, instead of fixing the frame, we'll fix the slider's guide, link 4. The crank still turns, and the connecting rod still moves, but now the whole assembly oscillates back and forth like a pendulum. We have the same exact parts, but now it's a pendulum pump, or something called a bull engine. Same parts, totally different machine. Okay, let's get even weirder. What if we fix the connecting rod, link 3? This is wild. The crank now revolves around one end, while the piston slides inside its cylinder, and the cylinder itself oscillates back and forth. This creates an oscillating cylinder engine. Again, the very same 4 links, just holding a different one still, creates a third, completely distinct machine. It's incredible. You know, once you understand these basic principles, you really do start to see the world differently. Complicated machines are no longer a mystery. They're just sentences written in the language of motion. So let's just recap the whole thing. You start with your alphabet, the links. You connect them to form pairs. You assemble those pairs into a constrained chain. That's the grammar. And finally, you fix one link to create a mechanism, a complete mechanical sentence that performs a task. I absolutely love this quote from one of our sources because it just nails the idea. A mechanism is the skeleton outline of the machine. It's so perfect. The mechanism is the pure skeletal logic of the motion. The actual machine is what you build around that skeleton to handle all the real-world forces and do useful work. So the next time you see a piece of construction equipment, a desk lamp, or even your car's windshield wipers, take a closer look. You now have the tools to read the language they're written in. Now that you know the grammar, what machines will you start to read?